Hello student, welcome to our physics discussion, that is physics in a smart way. We go into a topic that is usually branded as electromagnetics, that is combined electricity and magnetism. As the history of the topic goes, earlier maybe before the um, coming of great minds in physics like Albert Einstein and his contemporaries, it was thought that electricity is a separate topic and magnetism is another topic. But later on, people came to realize, people means those wise people there, they came to realize that electricity and magnetism, they are not separate. They are just two sides of a coin, just like you see a coin and head and tail. On one side that is electricity and second side that is magnetism. The same thing sometimes that manifests as electricity, pure electricity, and the same issue, the same fact that sometimes manifests as magnetism. It only depends upon the reference frame or observer. However, we shall be considering all those things because definitely if you are a serious student of physics, you must be interested and that helps in your growth or in the real understanding. Solving some problems, going through books like NCERT and all that, that doesn't, they do not complete your study, they do not complete your understanding. Okay, so I am going back to the time of your Newton's law. When you started to study Newton's law, there the concept of force was introduced. Newton was the first person to use the term force. We could come to know that there is a physical quantity known as force. But the type of force you are considering in the context of Newton's law immediately thereafter was a contact force. A contact force. Contact force means you pull a body, you push a body. If you pull a body or push a body, then you have to be in physical contact. You may tie up the body with the help of a thread or a rod or something like that, but that thread and rod makes you to be in physical contact. You kick somebody. So all those forces which come just after your um, that is introduction to the Newton's law, Newton's first law, second law, and third law, those are known as contact forces. Those are known as contact forces. But later on, when you slowly go over and cover the topics, you come to the topic of gravitation. And in case of gravitation, there you come across a force which can be transmitted or the force which can apply on a body without physical contact. Without physical contact. All those things earlier, they used to be described as action at a distance. Action at a distance. And when you say action, that is not drama or something like that. Force. Force at a distance. That means without being in physical contact, the force can be applied. Just like in case of gravitation, you know, a mass m1, it can attract another mass m2, even if there is some substantial separation between them. If the separation is anything less than infinity, then m1 will be pulling m2, m2 will be attracting also m1. So those forces acting on m1 and m2, so they are branded as action at a distance. There, the forces act on the body without any physical contact. So when wise people, they started to explain, because those ideas, sometimes a student may be in a difficulty because he or she may feel that they are going against our previous idea of contact force. So to explain all those things, people or wise people, they created the idea of the field. Field. Field means gravity field, electric field, and magnetic field. So they used to say that if a mass is there, then mass has got gravity field around it, and the gravity field is supposed to extend from the mass to the infinity and all that. Any other mass that is coming in, okay, that will be attracted. That will be attracted. Similarly, electric field, similarly, magnetic field. So when you introduce the idea of the fields, then all those things, all those forces which can act without any physical contact or so-called action at a distance, they can be very easily explained. They could be very easily explained with the help of the idea of the fields. Maybe gravity field, electric field, and magnetic field. All the three fields will be, you will be coming in contact. You will be coming across in your study of class 12. Okay. So before going to the issue any further, let us say we consider a thought experiment. There is a question, and that is like this. You will be asked a question, but don't worry. Think freely and think clearly. Maybe you are correct, maybe you are wrong, doesn't matter. But you must be trying to find the answer. There is a case where there is a mass, a pure mass. We know mass cannot stay without charge, charge cannot stay without mass, but at present we cannot make our issue complicated. We consider a pure mass. And there is a charge. There is a charge, and when I say charge, that's a pure charge. If the charge is having some mass, then you ignore that. You neglect that. The question is, will there be a force of interaction between this pure mass and this pure charge? This thing we brand as case 1. The question is, will there be a force of interaction, or will the mass exert any force on the charge, or charge exerts any force on the mass? We have to simply answer yes or no. That is case 1. We go to another case. There is a pure charge. Pure charge. If the charge is having some mass, we ignore that. There is a magnetic substance. A magnetic substance. Okay. Now the question is, will there be a force of interaction? Will there be a force of interaction between these? Okay, that we brand as case 2. Okay, in case 3, there is a pure mass and there is a magnet, a magnetic substance. Magnetic substance may be having some mass, but you neglect the mass effect. Again, the same question, the mass and the magnet, will there be a force of interaction between these two? So in all the 3 cases, the force is asked to be found out. Okay, think about, pause the video, think about the cases, and you have to think seriously and try to find the answer. Okay, but I cannot stop the video, I must continue. So you must give it. Okay, in all the cases, if you ask me of the answer, in all the cases, there is no force of interaction. Here the force is 0, here the force is 0, here the force is 0. Okay. You may ask why. Here explanation can be in a way like this. This mass, it has got its own gravity field. And this charge has got its own electric field. When the mass is kept near the charge, when I say near, you should not mean it very near or closing to each other, any distance less than infinite. So the mass, and theoretically, the gravity field and electric field, as you do know, they end at infinity because all the forces, they are inverse square forces. All the forces, they vary with vary with 1 by square of the distance, and the force will be zero only when distance tends to be infinite. Then only the force tends to be zero. So theoretically, the spread of gravity field around this mass, however small and big the mass may be, doesn't matter, is infinite. This charge similarly has got its electric field, and that extends up to infinity. So when we are keeping a mass near a charge, near the charge, their fields overlap, their fields overlap, their fields intersect, but there will be no force of interaction because gravity field doesn't recognize electric field, neither electric field doesn't recognize gravity field. A gravity field can interact, or there can be a force of interaction when gravity field, it interacts or intersects another gravity field. We got a mass m1, mass m1 has got its own gravity field. We got another mass m2, m2 has got its own gravity field. So when two similar fields, they do interact, they recognize each other, only then we see a force of interaction. Similarly, if you put a charge near another charge, they have got both their electric fields, and electric fields recognize each other, and when the fields intersect or when the fields overlap, there is a force of interaction. There is usually a force of interaction. The same thing happens with magnetism. So here, because here this is the mass and that is the charge, so gravity field and electric field, they are overlapping, they produce no force of interaction. In case 2, the charge has got its own electric field and magnet has got its magnetic field. Even if their fields are overlapping or intersecting, they are two different fields. This is electric, that is magnetic, so the force of interaction will be zero. The third case is similar. Mass has got its own gravity field, magnetic field, though they overlap, though they so to say intersect each other, but because they are different type of field, there is no force of interaction. So force will be zero, force will be zero, the force will be zero in all the cases. In all the cases. Okay, I think we have made it clear. So now let me remove the space between those things. We shall consider many different issues and all those things. The topic here is the first topic under electromagnetics, so far as my knowledge goes, is the force on a moving charge. Force on a moving charge inside a magnetic field. Inside a magnetic field. That is usually the first topic if somebody discusses anything in electromagnetics. So far as our syllabus, curriculum, books are mentioned, the force on a moving charge inside in a magnetic field. Okay. So when people did start to the so to say start to interact, or we may say experiment with the electric current and the bar magnet and all those things, we know those things and those implements were available to the early researchers. So they could find out that whenever a current carrying conductor is there that carries a current, the symbol of electric current is I. You may use a capital I or small I, doesn't matter. And we keep a needle magnet. A needle magnet you must have seen at your school laboratories. Near it freely suspended, the needle magnet was seen to be deflected, disturbed. So that made those early people, wise people in the past, to wonder why a needle magnet is deflecting or behaving erratically near a current carrying conductor. We know a current carrying conductor that is supposed to be consisting of, or that is supposed to be full of moving charges, especially we know electrons do move. So a current carrying conductor can be replaced by a stream of moving charges. So when they are present near a needle magnet, or when a needle magnet is present near them, the magnet seems to be disturbed. If the magnet is disturbed, immediately we think of Newton, we think of the force. We know force causes all those disturbances, or there is an interaction. And if those moving charges, they are having an effect or force on the needle magnet, as per Newton's third law, needle magnet must be having an effect on them. We may not be able to measure that force, we may not be able to visualize that force, but automatically we know Newton's third law is a fundamental rule that cannot be invalid. So if those moving charges, they exert a force, they disturb the needle magnet, orientation of the magnet by exerting a force, the needle magnet must be exerting a force on them. So basically, we come to the issue that we know needle magnet has got its magnetic field all around, and within that field, moving charges are there. So if such a thing happens, we know there is an interaction, there is a force which acts on both of them. So basically, we come down to the topic, we come down to the issue, that is the force on a moving charge if it is present inside a magnetic field. Okay, so thereby, let us say we consider a magnetic field and we consider a moving charge. The presentation of magnetic field, as you know, you might have known, is with the help of field lines. With the help of field lines, okay, that is the magnetic field, because a field can never be seen. So with the help of lines of forces or field lines, we visualize or we present a field. If you are not able to see it, as I told you earlier, before in electricity, then it is very difficult to contemplate a thing, because if you do not create a mental image, then it will be very difficult to think of something. The magnetic field is usually the field strength or intensity, whatever it is. In electricity, we know a very, very significant quantity, that is electric field intensity, is usually a vector that denotes the strength or weakness of the electric field that is present here. Electric field strength, electric field intensity. So similarly, in case of magnetism, there is a quantity which is known as magnetic induction. This quantity B, you might have known that is magnetic induction. And if you do not know, then consider it a quantity just like electric field intensity, then your problem will be slightly over. Magnetic induction, and B, the symbol is capital B, just like electric field, that's also a vector that presents or that behaves, or that is the repetitive, just like electric field does, electric field intensity does in case of electric field. This B is known as magnetic induction. Okay, electricity and magnetism, they have got many similarities and some dissimilarities also. So E हमारा जहां पर था, wherever E was there, we replace E by B. B does the same role here. What to do? We consider a charge, and you know, for test purposes, usually we consider a positive charge, that's a convention. Charge is Q, and we make it to move inside the magnetic field. Let us say the charge is moving with a velocity V. So as you have discussed, whenever the charge comes into the magnetic field, there will be a force on the charge, and there will be a force on the field also, on the field creating body. Initially, we don't take the second. How much is the force acting on the field or a field creator and all that. Basically, we are interested how much is the force acting on the moving charge. That is our prime interest now. Okay. So if we try to find the force that acts on the moving charge, whenever it's inside a magnetic field, I'm sorry, I forgot something to tell you, the so-called the idea of the fields. So here the question comes that our experimenters, they have found that when a current carrying conductor is placed near a needle magnet, the force acts. But if you try to explain why the force acts, why there is the interaction between the needle magnet and the current carrying conductor, or here translating that into this situation, that why a charge moves, why when a charge moves inside a magnetic field, there is a force acts upon that. Only one explanation can be given, that somehow we do not know till now. Physics is not able, has not been able to solve this thing, that somehow when a charge moves, somehow due to some mysterious things, the charge, because it's a charge, it will be having its electric field. But due to the motion, in addition, and magnetic field will be there around the charge. The charge acquires some magnetic properties. The moment the charge acquires some magnetic properties, then you know that is somehow magnetized. We may crudely say that, or there will be a magnetic field around it. If you compare this charge with a charge at rest, we know that thing was not visible. If you keep a needle magnet near a static charge or the charge at rest, you may keep them for 5 years or 6 years. No force of interaction was seen. That has been confirmed by our early experimenters. But the moment the charge starts to move, the moment the charge has got a motion does such mysterious things we have not been able to explain it till now. The charge is seen to acquire a magnetic property or a magnetic field that gets developed around it. So now the moving charge had got its own magnetic field, and it is present inside another magnetic field, which is presented by B, or magnetic induction. So because both are magnetic fields, obviously there is a force of interaction. We can explain it like this. Okay. Okay. Am I clear? Okay. So now we have gone through the issue why a moving charge will interact with a magnetic field. As you can see, if you go through our books, they express the force by an expression Q into B cross B. When our teachers, they start to teach that force on a moving charge, when that moves inside the magnetic field, the force equal to this. But usually the student is puzzled. And if you ask me, then I can say that is directly the murder of physics. That is virtually the murder of physics, because physics is logical. Physics is a topic which is to be understood. If a teacher says F equal to, oh, students, you just remember F equal to Q into B cross B and all that, why the student will accept that? And if a student accepts that readily like a meek lamb, then that is against all the spirit of physics, because physics is all about questioning why, how, every time. So, but unfortunately, our books and our teachers, whatever it is, I should not talk against somebody. My aim is not like that. But sometimes I am pained that here the thing that suffers is physics, and inquisitiveness of the student, everything is murder. You can see the effect. You can see the effect. Beyond 1970, our education system, especially in India, India has got 1/6 of the population in the world, but we have not been produced a Nobel laureate in physics. We have not been produced a Nobel laureate in physics, neither a field medal in mathematics. And then the basic thing is that we put great emphasis on rote learning, book learning, and with the help of that, and with the things like that, situation like that, things cannot improve. Okay, that is a thing to be ashamed. I usually, when I talk to some teachers, when I talk to some students, I raise this question, but nobody bothers. Okay, so if such type of teaching will be helping us in making the India's progress in pure science, in engineering, or in pure topics to grow, then that is a hope against hope. Anyway, let us come back. Because I'm a teacher, it is my habit to give speeches to students. I should not do that. Our topic is left behind. So they express the forces like this, but we should not believe in that thing if we are not convinced. If we are not convinced. So what to do? We try to find that expression using our common sense. Here two things are required. One is your common sense or scientific sense, and second is the job of or the result of our early experimenters what they did find. If you combine the two things, we'll be able to arrive at the conclusion. Okay, so just we use our common sense or our logical sense and try to find out how or what can be the so-called expression of the force or how to find the force. We are just so to say investigating the issue. If you try to use logic here, we know the force must be depend on the charge. The force must be dependent upon velocity. The force must be dependent upon magnetic field. Here you may question, why the force will be proportional to charge? Why not square root of the charge? Why not the square of the charge? Similarly, the power, different powers of velocity and all that. This we borrow from our experimental results, that it has been seen when charge is double, the force is double. When B is tripled, the force is tripled. Similarly, the magnetic field, if the external magnetic field is stronger, even on the same charge, moving with the same velocity, is supposed to have a stronger force. So from experiment, we find out our common sense says the force must be depending on the charge, must be depending on velocity, must be depending upon B. But you take the help of, we bank upon the help of our early experimenters, and they have already seen that when the charge is increased, the force gets proportional increase. The same thing happens with velocity, the same things happens with magnetic field. There is no other quantity which you have to consider. So now we say, logically you can conclude that force must be proportional to Q, V, P. Okay, Q into V into B. So next statement should be that F equal to a proportionality constant into Q into V into B. Okay. So far as the quantities involved in this expression, we know earlier we know about force, we know about charge, we know about velocity. Only thing that I have introduced here is a thing just like electric field intensity, that is magnetic induction. Our scientists are early pioneers in this field. They were really intelligent fellows. They have found the SI unit of B in such a way that this proportionality constant is always reduced to 1. Of course, if the proportionality constant is not equal to 1, that becomes 2 or 3 or like that. That makes no great harm. That doesn't stop us in our progress, but they are so intelligent, they have made our job so easy that the unit of force, unit of Q, unit of V, they were earlier selected, and they select the unit of B in such a way that this proportionality constant is always used to 1. So now our job is easier because you do not have to consider the proportionality constant. That is always 1. So F equal to, that is Q into V into B. That is the way we see now. That is the point where we have reached. But one thing disturbing here, somebody who is seeing our derivation, listening to our idea, he may be having some doubt, he may be having some questions. He or she may say, okay, your expression seems to be an expression which banks only on magnitudes. And magnitude is a scalar quantity. Their question can be, in a way, okay, you people are considering such things. First is force is a vector, charge is a scalar quantity, but velocity is a vector. Magnetic induction, because it has got almost similar properties as electric field, that is a known vector. So their question will be, your expression is in a very odd way. You are saying that a force is equal to, you temporarily leave the charge, is basically on the right hand side, the product of two vectors, V and B. How you are going to write this? Two vectors cannot be simply multiplied. We know, you know earlier that when we multiply a vector with another vector, the multiplication job is not so easy. There are two types of multiplication. One is dot product. Second is cross product. So then immediately the question asks that why you are writing in such a lame way, in such a lazy way, in such a way that a student of physics will be offended. So then we immediately rectify ourselves. We know here the product between V and B must not be a simple arithmetic product, just like the product between two scalars. That must be either a dot product or cross product. If you decide that, we know this cannot be a dot product, because dot product usually yields in a scalar quantity, and here the yield is force. The multiplication here along with the charge gives a force. So that must be a cross product. If it is a cross product, then a student can be confused. It can be either V cross B or it can be B cross B. So again, you have to fall back upon our earlier experiments. They tried to find out the direction of the force, the direction in which the charge is deviating. That can very easily gives the direction of the force, the direction in which the force is acting. So their analysis says that the real formula will be F equal to your Q into V cross B, not B cross B. So they could see that the way the force acts, the force will be equal to Q into V cross B. So that was the formula which we got at last. That formula is in vector form. If we express that in the scalar form, we can also, you can also put it like that. Let me clear up some space. If F equal to V cross B, then we know we can also express the force magnitude. We can also express the force magnitude as, that is, Q into V magnitude into B magnitude into sine theta, because a dot product, a cross product always yields in sine theta, always is associated in sine theta. And now what is theta? We know theta is the angle between the two vectors, that is V and B. In the diagram, if you make the suitable presentation. We know that is the velocity direction, and these are the magnetic field lines. So angle between the velocity and magnetic field, or velocity and magnetic induction, B is in this way, that angle must be theta. That is the way, if you try to express the force magnitude. So student, that was the history of the development of the force on a moving charge inside a magnetic field. Okay, that's all for today. Think about that. Go to the video once again. You have to know all those things. Blindly accepting because the teacher says, because the book says F equal to Q into V cross B, that won't be at all healthy if you want to develop in physics, if you want to progress in physics. And theory is utmost essential. How many problems you solve, you just take some problems, 20 problems, Q is given, B is given, B is given, theta is given, and try to find the force. Idea won't be clear. Idea won't be. If you have gone for 10 questions, then 11 question can be really screwing you. Okay, so for that, the understanding of the concept, understanding of the idea will be, or is really essential. And whatever time it takes, whatever effort it takes, all those, they will be for your own benefit. Okay, you cannot dispense with that. You cannot avoid that and quickly go into physics. And mind it, there are some tricks. Sometimes student asks, there are some tips in physics. Sometimes student asks me, my answer will be yes, they are. But those tricks and tips can be employed by the person, by the student who understands the theory. If you do not understand the theory and goes for tricks and tips, then you can be in a real hell. It can be backfiring on you like anything. So I'll be giving you all those tricks and tips. I am quickly uploading some videos. Okay, you must excuse me in that way, but I'll be uploading, that is definite, and all those things. How to use all those things, how to use mathematics for our benefit, to avoid lengthy calculations, lengthy steps, and all those things, especially using calculus, how to avoid all those things. So those I'll be giving you in near future. So thank you again for your kind cooperation. Let us stop here, and if you like it, give me a like, please subscribe, and please share it amongst your friends. Okay, लंबा मीटिंग लंबा है लगे